Hi, everybody. This is your first video in section 2 of unit 3. So in this video, I'm going to talk to you about density curves, and I'm going to introduce the normal distribution to you, as well as talk about the empirical rule, the 68, 95, 99.7 rule. And then in the next video, we're going to get a lot more into normal probability calculations and how you use a normal distribution to figure out how likely something is. Okay, so all of this starts with density curves. Okay, what you're used to doing at this point is creating histograms, stem plots, dot plots, things like that. That's the way that we have right now to represent data. Okay, but a lot of data tends to follow an idealized pattern. Okay, and we represent that idealized pattern with something called a density curve. So you get a density curve when you take lots and lots and lots and lots of samples of a particular variable in a data set, right? It's like when you take a sample size and make it much, much larger, right? Eventually, the bins of the histogram will get smaller and smaller and smaller and smaller until really all you can see, all that's left, is the shape, right? The general shape of the distribution, which is what this red line is right here. Okay, that red line is the density curve here. Okay, so essentially what this is an idealized description of a distribution. Okay, and what's great about density curves is rather than having to count individual data points within, say, a histogram bin, or within one stem of a stem and leaf plot, or one marker on a dot plot, you can simply use the density curve and the rules of the density curves to calculate those probabilities. Okay, so there are a couple of main, like really just two rules that you have to remember for density curves. One of which is that the density curve is always on or above the horizontal axis. Okay, which is similar to most of the data that we've been working with at this point. Okay, and the other bigger, more important rule is that density curves always have an area of exactly 1 underneath. Okay, so have an area of exactly 1 underneath it. Okay, and the reason for that is because it encompasses 100% of the data. Okay, so what that allows us to do is, if we can think about the 100% of the data being underneath a density curve, right? Then that means the area under that density curve represents 100% of the data. Okay, so what we can do is figure out proportions of how likely something is to occur within specific boundaries using the area underneath the density curve. Okay, because we're talking about the overall pattern of the distribution, right? So the area underneath the curve, uh, within certain boundaries, right? Say less than a certain value on the x-axis down here, or greater than a certain value, or in between certain values. Okay, the so the area under the curve between 2 points, what that actually represents is the proportion of all observations that fall in that interval. Okay, and now density curves don't necessarily have to be normal or bell-shaped like this. Sometimes you will see density curves that are uniform, right? That look something like this. okay, where say you range from 0 to 4, right? Which means that this height up here has to be 1/4, so that the entire area, which equals base times height, so that the entire area is equal to 1, or 100%. Okay, so you may see some that look like this that are uniform, right? So think, for example, if we took this uniform distribution and I wanted to know, okay, so here's say 1, 2, 3, and then 4 there. Say I wanted to know what's the probability that I land between that I land between 1 and 2. Okay, well, that probability, if I wanted to shade where that area occurred, it's right here between 1 and 2. Okay, my area here is base times height. So the base now has a length of 1, and the probability is still 1/4, right? So I have a 1 in 4 shot, right? The way you kind of want to think about density curves is they're almost like dartboards, right? Where you have a certain amount of area that you're trying to hit, right? And what we are calculating with density curves is how likely is it if I just like shut my eyes and threw a dart at that dartboard at random, how likely is it that I would land in a particular interval, or less than a certain number, or greater than a certain number? Like, what's the probability that I would land just in this like orange part that I have shaded in versus other parts on the outside? Okay, most of the density curves that we're going to be looking at will be bell shaped like this one and normally distributed. Okay. So the next thing we have to talk about is, well, okay, great, I have these density curves. What do I do with them? And how do I figure out all of these calculations, right? So the cool thing about the rules here is that they're exactly the same rules that we learned in the last unit, right? Which I'm hoping kind of makes sense to you, because in a lot of the things that we did in the last unit, I would make you draw curves over the top of a data set to figure out what the shape was and to see if you could figure out where the skew was. Okay, so it's the exact same rules as the last unit. Okay, the median is still the equal areas point. Okay, right? It's still the exact middle data point, right? And we're just thinking of it here in terms of area, right? So it's the equal areas point, meaning that half of the data is to the left of the median and half of the data is to the right of the median. So 50% to the left, 50% to the right. Okay. The mean, how we describe the mean is we call it the balance point of the data. Okay. And just like the last unit, skewed distributions will have a mean that is pulled towards the tail. So if you have something that is skewed to the right, if you have a density curve that is skewed to the right, like this one, okay, the mean is going to be pulled towards the right, towards the tail. Okay, if you have a density curve that is skewed to the left, okay, the median may be here, for example, in orange, but the mean may be here, okay, being pulled towards the tail. Okay, same thing. For us, for this unit in particular, right, we're mostly dealing with the normal distribution. So normal and symmetric distributions will have the same mean and the same median. Okay, mean and median are exactly the same. Okay, and we use a couple of Greek symbols to represent mean and standard deviation in a density curve. Okay, the reason we use Greek letters here is because density curves usually are talking about the population value, which is the true value, right? Versus the sample values, right? So in the last unit, especially when you would run statistics on your calculator, you probably remember seeing symbols like this, like mean would be represented with X bar, and then standard deviation would be represented with an S, maybe with an X subscript underneath it, okay? We use these symbols because we were dealing with samples. These are sample symbols. Okay, because density curves are an idealized version of the distribution. That's like your population version of the distribution. It's the true value. Remember, the population values are the truth, right? This class is about a search for the truth. So when we're dealing with density curves, typically we're dealing with population data, right? And the general trend of population data. So we use the fancy Greek symbols. So the fancy Greek symbol for mean is this weird looking U thing. It's like a U with a tail, right? And it's called mu, right? And it means average or mean, okay? And then standard deviation, we use this little O looking symbol with a tail sticking out the end. Okay, so it looks like this, and it's called sigma. Okay. All right, so let's look at a practice problem or two. Let me clear this guy off. Okay, so here we have some practice here. So I know this picture is a little bit hard to see because I had to take a picture of it like from the textbooks. Like I couldn't scan it and the light was a little bit off. But in any case, so the question here first is, why does this curve fit the definition of a density curve, right? So you just have to go back up to the definition of a density curve, which is these rules right here. Okay, and see if this curve satisfies both of those, which it does. Okay, so the entire curve is above the horizontal axis. Okay, and the area under the curve is 1, which is what you want. Okay. Question 2 says, what proportion of observations lie between 7 and 8? Well, you can see that written directly on the document here, right? So 7 and 8 is this interval here, right? And you can notice, hopefully, that this area is shaded a darker green, and they tell us what the area is. So remember, the area between two numbers is the same as the probability of landing, quote unquote, in that area. Okay, so the proportion of observations that lie between 7 and 8 is 0.12, or you could say 12% if you wanted. Most of the time, in statistics, we write things with decimals or percentages rather than writing them with fractions. It's the way it works most of the time. Okay, then the last question here is, which of these is greater, the mean or the median? Okay, so in order to figure that out, we have to look at the skew, right? So I would say the mean is probably about here in red. Okay, that's probably where the median is, or close enough, right? It looks like about half of the curve is to the right of that and about half is to the left, which is what we want. But this distribution is skewed to the left, right? Because the tail is being pulled to the left, which means the mean is probably around here, right? Being pulled towards the tail. So the value that is greater in this distribution is the median, okay? Right? So the median is greater because the mean is being pulled towards the left skewed tail, making it less than the median. Okay, all right, so that's your overview and general like introduction to density curves. Okay, the density curves that we care the most about in this unit, however, are normal distributions. Okay, right, normal distributions and normal density curves. Okay, so these are your typical bell curved shaped data. Okay, and we calculate probabilities with them using normal density curves, right? Most data is not going to fit the normal curve exactly, but it's close enough that we can use the normal density curves to describe these data sets and calculate these probabilities. Okay, so normal distributions are symmetric. Okay, single peaked, meaning there's just that one peak in the middle and then bell shaped. Okay, because we know that all normal distributions look like a bell, right? They look bell shaped, then that means we don't have to describe their shape, right? Because we already know what it looks like. There's a general understanding in the statistics community of what a normal distribution looks like, okay? No matter what the data set is. So we can describe normal distributions or name normal distributions using only the mean and standard deviation, okay? In normal distributions, the mean and median are always the same, okay? And you'll sometimes see normal distributions expressed this way. This is also how you plug some information into your calculator in order to calculate some of these probabilities. So the capital N stands for normal. There again is that mu, which is the mean, okay, and the standard deviation that comes after it, the sigma, all right? So in the next part of this video, I'm going to talk to you about the 68, 95, 99.7 rule. So give me just a second to clear my screen off and do some rearranging, and then I will be right back. All right, folks. So the last part of this video here is on the 68, 95, 99.7 rule, which is also called the empirical rule. Okay, the empirical rule states that in any normal distribution, no matter what the mean is, no matter what the standard deviation is, as long as it's a normal distribution, then 68% of the data, of the observations, lies within one standard deviation of the mean, right? So that's what this means, right? This means one standard deviation of the mean, okay? 95% of the data falls within two standard deviations of the mean. So meaning you start at the mean, go two standard deviations above, and then two standard deviations below. And then 99.7% of observations fall within three standard deviations of the mean. Okay, so in most normal distributions, you can capture almost all of the data if you go three standard deviations below the mean and three standard deviations above the mean. You're not going to have very much data left over that's further away from the mean than that. Okay, so because this rule works no matter what type of distribution you are dealing with, or not what type of distribution, but rather what like what mean and what standard deviation you're dealing with, it works no matter what, as long as it's a normal distribution. Okay, what that means is that if we have some values, if we know the mean and standard deviation, then we can calculate how likely is it to fall within a certain interval, or fall below a certain value, or above a certain value. Okay, so that's what we're going to do in this question right here. Okay, so we are dealing with a distribution of batting averages that is normal with a mean of 0.261 and a standard deviation of 0.034. So the first question here says, sketch a normal density curve with the batting averages and then label the points that are 1, 2, and 3 standard deviations away from the mean. Okay, so first thing you do is draw a line straight across and then sketch your normal distribution. It does not have to be beautiful. It just has to look fairly symmetric and look like a bell curve. Okay, whenever you draw these, you always want to draw a line down the middle because that's the mean. Okay, and then put the standard deviation as a little symbol off to the right-hand side, and then write what the standard deviation is, which is 0.034. Okay, so this is my mean right here. And each tick mark that I'm drawing represents one standard deviation difference, right, going up and down. Okay, so here, this tick mark here is one standard deviation up. This one is 2 standard deviations up, and this one is 3 standard deviations up. Then going the other direction, going to the left, this tick mark here is 1 standard deviation down. This one is 2 standard deviations down, and this one is 3 standard deviations down. Okay, so what we want to do now is actually label these with the numbers that we have. Okay, so I know my mean is 0.261. Okay, then in order to go up and to the right to get what these values are, the 1 standard, 2, and 3 standard deviations up, what I'm going to do is I'm going to add the standard deviation to this number. So add 0.034, and then you're going to get this next number here, okay, which is 0.295. Okay, then I'm going to do the same thing again, right? I'm going to add 0.034 to this value, right, and just keep going, right? So 0.295 plus 0.034 is 0.329. And then I'm going to add that standard deviation one more time to get to 3 standard deviations up. So 0.329 plus 0.034 is 0.363. Okay. To go the other direction, okay, so to go the other direction, hold on, I need my eraser here. Okay, so to go the other direction, rather than adding that standard deviation, I'm going to subtract it, right, to go down the number line, right? So when I do that, if I do 0.261 minus 0.034, I get 0.227. If I subtract again, I get 0.193. And if I subtract a third time, I get 0.159. Okay, so there's my labeled normal density curve. Okay, number 2 says, what percentage of batting averages are above 0.329. So whenever you're doing these things, you always want to draw a line where your boundary is. This number that they give you is your boundary. And they say, I want to go above 0.329, which is this area here. So it's always a good idea to shade the area that you're looking for, okay? So 0.329 is on the 2 standard deviations marker. So according to my data, right, and according to my rule, 95% of my data is here between -2 and +2 standard deviations. Okay, so if you have 95% in the middle, that means you have 5% left over in the tails. Okay, now that does not mean that this shaded area is 5%. It's 5% in both tails together. Okay, so that means, since this is symmetric, that the area is the same in the 2 tails. So that means there has to be 2.5% in each tail. Okay, so this, the 2.5%, that is the probability that x is greater than 0.329. Okay, so we used our normal distribution to calculate a probability, right? Okay. We can do the exact same thing with a different interval. So I have between 0.193, which is here, and 295, which is here. Okay, so this one's a little bit trickier because I have one marker at -2 standard deviation, so it's a 2 standard deviation, and I have one at a 1 standard deviation. Okay, so I kind of have to think about this. There's a couple of different ways that you could solve this, either by using addition or by using subtraction. So I'm going to use the addition method, right? Saying, okay, between -1 and 1 standard deviations is 68%. Right? And all I'm missing is this area here between -2 and -1 standard deviations. Well, I know that between 2 standard deviations, so there's 95% of the data within 2 standard deviations, and there's 68% within 1 standard deviation. So if I subtract those, okay, I end up with 27% of my data, and that is between -2 standard deviation and -1 standard deviation, and between 1 and 2 standard deviations together. Okay, just like this 5% up here was not 5% in each tail, it was 5% in the 2 tails together. So there's 27% of the data in this area and this area combined. So I need to figure out just what one of those areas is. Okay, so to do that, so to get just this, okay, I'm going to take my total, 27%, and cut it in half. So I get 13.5%. So that means my total probability is 13.5 plus 68, right? Which is 81.5 when you add all that together. So 81.5% of the data falls between 0.193 and 0.295. Okay, and the way that you would write that, I'm going to write it up here in this blank space because I've run out of space down here. So the way that you would write that is the probability that x is in between 0.193. So 0.193 is less than x is less than 0.295, right, with your boundaries. And then you would either give a percentage or the decimal value. So you can say either 0.815 or you could say 81.5%. Now, this notation is very important. Without it, these numbers, the 0.815, have no meaning whatsoever. I have no idea what 0.185 is supposed to be. 0.185 what? 0.185%, 0.185, is that the probability? Is it the standard deviation? Is it the mean? Like, I have no clue, right? Unless you use that probability notation and you tell us that that's exactly what you're trying to find, okay? Rather than having to write out that the probability of uh, batting averages being between 0.193 and 0.295 is, and then giving your answer, you can just write it in that math notation, and it's much simpler, much shorter, right? And the AP readers will know exactly what you mean. All right, y'all, so that is it for this video, and I will see you in the next one to dive really deep into z-score calculations and standard normal curve probabilities. Bye, everybody.